Tonight, we're going to explore one of the most haunting discoveries in modern astronomy: planets that drift through the galaxy alone. No sun to orbit, no parent star to provide light or warmth, just endless darkness and the cold void of interstellar space. These aren't planets in the traditional sense. They're orphans, ejected from their birth systems, cast out into the darkness to wander the galaxy for billions of years. And here's what will change how you see the night sky. There might be more of these rogue planets drifting through our galaxy than there are stars. Think about that for a moment. For every sun you can see, there could be dozens or even hundreds of invisible worlds floating through the darkness between the stars. Worlds as large as Jupiter, worlds with moons, worlds that might even harbor life in their frozen depths, completely independent of any star. By the end of this journey, you'll understand not just what rogue planets are, but why they matter, how many exist, and what they reveal about the violent chaos of planetary system formation. Before we dive deeper, if you find this exploration fascinating, a quick like or subscribe really helps the channel grow. It makes a huge difference for me. Now, let's begin our journey into the darkness between the stars. Let's start with something fundamental that took humanity thousands of years to understand. What is a planet? For most of human history, the answer seemed obvious. Planets were the wandering lights in the sky that moved against the fixed stars: Mercury, Venus, Mars, Jupiter, Saturn. The word planet comes from the Greek planetes, meaning wanderer. But these wanderers all had something in common. They orbited the sun. When we discovered exoplanets, planets orbiting other stars, we simply extended the definition. A planet orbits a star. That seemed like the essential characteristic. But in 2000, everything changed. A team of astronomers using the United Kingdom Infrared Telescope in Hawaii was surveying a star-forming region called the Orion Nebula, about 1,300 light-years from Earth, roughly 7.6 quadrillion miles, or approximately 12.3 quadrillion kilometers. They were looking for young brown dwarfs, objects too small to sustain hydrogen fusion like stars, but larger than planets. What they found was something unexpected. Objects with masses clearly in the planetary range, between 5 and 15 times Jupiter's mass, floating freely in space. No parent star, no orbit, just drifting through the nebula. At first, astronomers debated whether these were actually planets or just very small brown dwarfs. After all, if they never orbited a star, could they be called planets? But as more observations accumulated, a picture emerged. These objects had formed in the same disk of material that creates planetary systems, but something had gone wrong. They'd been ejected, cast out from their birth systems through gravitational interactions. They were planets in every physical sense: similar composition, similar formation mechanism, similar internal structure. But they had no sun. They were rogues, orphans, drifting alone through the galaxy. The discovery immediately raised an important question. How common are these objects? Was this a rare anomaly, or was the galaxy filled with unseen worlds floating in the darkness between the stars? To answer that, we need to understand how planets form, and critically, how they can be kicked out of their systems. The story begins in vast clouds of gas and dust scattered throughout the galaxy. When a star forms from a collapsing cloud of gas, it doesn't consume all the available material. About 1 to 2% of the mass ends up in a rotating disk around the young star. This disk is where planets are born. Dust particles in the disk collide and stick together. Electrostatic forces and gentle collisions cause them to grow from microscopic grains to pebbles, then to boulders, then to kilometer-sized planetesimals. This process is called accretion. Eventually, some planetesimals grow large enough that their gravity dominates. They begin pulling in material from a wider region, growing rapidly into planetary embryos. Within a few million years, you have rocky planets in the inner system and gas giants farther out, where it's cold enough for ice to exist. But here's the critical part. This process is messy and chaotic. A typical protoplanetary disk might form dozens of planetary cores. These cores interact gravitationally, they perturb each other's orbits, they migrate inward or outward as they exchange energy with the disk of gas. Sometimes these gravitational interactions become violent. Two planetary cores might pass close to each other, and in that moment, their gravitational interaction can fling one of them onto a completely different orbit. If the interaction is strong enough, one planet can be ejected entirely, sent flying out of the system at speeds high enough to escape the sun's gravity. Computer simulations of early planetary system formation show this happening frequently. Create a system with 5 or 10 Jupiter-mass planets and let them interact gravitationally for a few million years. More often than not, some get ejected. The survivors settle into stable orbits, becoming the planets we detect around other stars. But the ejected ones, they become rogues. This isn't speculation. We see evidence of this violence in our own solar system. Neptune and Uranus are in orbits that are difficult to explain unless they formed closer to the sun and then migrated outward. Something pushed them, most likely gravitational interactions with other planets or with Jupiter.
Some models suggest our solar system once had additional giant planets that were ejected billions of years ago. They might be out there right now, dark and invisible, drifting through the Milky Way. Former members of our solar system, cast out into the void. The first challenge in understanding rogue planets is detection. How do you find an object that emits no light and drifts in the darkness between stars? You can't use the methods that work for normal exoplanets. The transit method, watching for the tiny dimming when a planet passes in front of its star, doesn't work. No star means no transit. The radial velocity method, detecting the wobble a planet induces in its star, doesn't work. No star means no wobble. But there's one method that can work: gravitational microlensing. Einstein's general relativity tells us that mass warps spacetime. Light traveling through warped spacetime follows curved paths. If a massive object passes between Earth and a distant background star, the object's gravity can bend the star's light toward us, briefly making the star appear brighter. This is called gravitational lensing. For stellar mass objects, the brightening can last weeks or months, but for planet mass objects, the lensing event is much briefer, lasting only hours or days. This is microlensing. Astronomers have been conducting microlensing surveys for decades, monitoring millions of stars toward the galactic center where stars are dense enough that alignments happen regularly. Most lensing events are caused by stars, but occasionally they detect an event caused by something much smaller, a planet. If the planet is orbiting a star, the lensing signature shows two peaks, one from the star and one from the planet. But if the lensing shows only a single peak from a planetary mass object with no stellar companion, you found a rogue planet. In 2011, a team led by Takahiro Sumi analyzed data from the microlensing observations in astrophysics survey. They found 10 microlensing events consistent with Jupiter mass objects without host stars. Based on the survey's sensitivity and the number of events, they calculated that there are roughly 2 free-floating Jupiter mass planets for every star in the Milky Way. Let me repeat that. For every star you can see in the night sky, there are at least 2 Jupiter mass rogue planets drifting unseen in the darkness. The Milky Way contains about 200 billion stars. That suggests 400 billion rogue planets in the Jupiter mass range alone. But that's just the beginning. Microlensing is only sensitive to relatively massive planets, those roughly Jupiter's mass or larger. Smaller planets produce weaker lensing signals that are harder to detect. The surveys likely miss most Earth mass rogues and smaller objects. In 2021, astronomers using data from NASA's Kepler Space Telescope during its K2 mission analyzed microlensing events and found evidence for even more rogue planets, extending to lower masses. Their analysis suggested the population might be even larger than previous estimates, potentially trillions of rogue planets in the Milky Way. Trillions! The galaxy might contain several times more rogue planets than stars. The space between stars isn't empty, it's populated with invisible worlds, orphans of planetary system formation, each one a failed member of some long-ago planetary system. Think about what this means. Right now, as you're reading this, hundreds or thousands of rogue planets might be passing through the volume of space within a few light years of Earth. you'll never see them. They emit almost no light and produce almost no heat detectable from Earth. They're phantoms, invisible wanderers. The nearest rogue planet might be closer than the nearest star system. Proxima Centauri is 4.2 light-years away, roughly 25 trillion miles, or approximately 40 trillion kilometers. But a rogue planet could be only 1 or 2 light-years away, and we'd have no way to know unless it happened to pass directly in front of a background star during a microlensing survey. This realization transforms how we think about the galaxy. We imagine space as mostly empty, with occasional points of light marking stars and their planetary systems. But the reality is far more crowded. For every visible star system, there are multiple invisible worlds drifting in the darkness between. Now, let's consider what these worlds are actually like. What happens to a planet when it loses its star?
Imagine standing on the surface of a rogue planet. This is purely hypothetical, of course. You couldn't actually survive there, but let's imagine. The first thing you'd notice is the darkness. Not the darkness of night on Earth, where the moon and stars provide some light. Absolute darkness. The kind of darkness that would make the deepest cave on Earth seem bright by comparison. There's no sun. No star provides warmth or light. The only illumination comes from distant stars, and they're so far away that their combined light is millions of times dimmer than moonlight on Earth. You couldn't read by it. You couldn't see your hand in front of your face. The second thing you'd notice is the cold. Unimaginable cold. Without a star, the planet receives almost no external heat. The only warmth comes from the planet's interior, from radioactive decay of elements like uranium and thorium in the core, and from residual heat left over from the planet's formation. For a Jupiter-mass rogue planet, the surface temperature would be around -370 degrees Fahrenheit, or about -220 degrees Celsius. That's cold enough that nitrogen and oxygen, the main components of Earth's atmosphere, would be frozen solid on the ground. For an Earth-mass rogue planet, the situation is even extreme. Smaller mass means less residual heat and less radioactive material. The surface would cool to near the temperature of interstellar space itself, around -454 degrees Fahrenheit, or -270 degrees Celsius, just a few degrees above absolute zero. Any atmosphere the planet once had would freeze out and fall to the surface as ice. Water oceans would freeze instantly, creating a layer of ice potentially hundreds of kilometers thick. The surface would be a lifeless, frozen wasteland. Or would it? Here's where things get interesting. While the surface of a rogue planet would be frozen and dead, the interior could be a different story. Earth's internal heat comes from two sources. Radioactive decay provides about half. The other half comes from primordial heat, warmth left over from Earth's formation 4.5 billion years ago, when gravitational energy from accreting material heated the planet. This internal heat drives plate tectonics, volcanic activity, and hydrothermal vents on the ocean floor. Those hydrothermal vents are crucially important because they support ecosystems that don't depend on sunlight. Chemosynthetic bacteria derive energy from chemicals in the vent fluids, and entire communities of organisms live around these vents in complete darkness. Now, consider a rogue planet that formed with a substantial water ocean. When it was ejected and lost its star, the surface froze. But beneath that ice, the ocean could remain liquid, kept warm by the planet's internal heat. Jupiter's moon, Europa, is an example close to home. Europa orbits in the cold outer solar system, far from the sun. Its surface is frozen ice, but tidal heating from Jupiter's gravity keeps the interior warm, and beneath the ice, there's probably a liquid water ocean tens of kilometers deep. Europa's ocean might harbor life, sustained by chemical energy from hydrothermal vents on the ocean floor, completely independent of sunlight. If life exists there, it would be surviving on internal planetary heat alone. A rogue planet could have the same situation, but on a larger scale. A rogue planet with Earth-like mass could maintain a subsurface ocean for billions of years, sustained by radioactive decay in its core.
Life could potentially arise and thrive in that hidden ocean, completely isolated from the rest of the universe. The planet would be orbiting the galactic center, taking hundreds of millions of years to complete each orbit. It would pass through different regions of the galaxy, occasionally passing relatively close to star systems, but never close enough to be captured. It would be a wandering biosphere, carrying its ecosystem through the void. This raises a profound possibility. Life in the galaxy might not be confined to planets orbiting stars. Rogue planets with subsurface oceans could harbor life, and there might be trillions of such worlds scattered throughout the galaxy. In fact, rogue planets might be among the safest places for life to exist over very long timescales. Planets orbiting stars face periodic threats. Their sun will eventually die, either swelling into a red giant and incinerating inner planets, or exploding as a supernova if the star is massive enough. Nearby supernova explosions can sterilize planetary surfaces with radiation. Asteroid and comet impacts are more common in systems with active planetesimal populations. A rogue planet drifting through interstellar space faces none of these threats. No stellar evolution to worry about, no supernova risk from a dying parent star, very low probability of impacts because space is so vast and empty. The surface is dead, but the subsurface ocean is protected, stable, potentially viable for life over timescales of many billions of years. Some scientists have speculated that rogue planets might be better incubators for life than planets orbiting stars. They're more common, they're more stable long-term, and any life that does arise would be protected from external threats. If this is true, then the majority of life in the galaxy might exist in darkness, in hidden oceans beneath the ice of rogue planets, completely invisible to us. We might be the unusual ones, living on a planet orbiting a star, dependent on sunlight. The typical living world might be dark, cold, and adrift in interstellar space. This is speculative, of course. We have no evidence that life exists on rogue planets, but the possibility is scientifically plausible, and it changes how we think about where to look for life in the universe. Let's talk about what happens during the ejection process itself, because understanding this helps explain the properties of the rogue planet population. When a planet is ejected from its system, the process is violent and dramatic. Imagine two Jupiter-mass planets in a young planetary system, both orbiting within a few astronomical units of their star. Their mutual gravity causes their orbits to change over time, sometimes bringing them closer together. If they pass close enough, within about 3 times the larger planet's Hill radius, the gravitational interaction becomes strong. The Hill radius is the distance within which an object's gravity dominates. For Jupiter, it's about 50 million kilometers. During a close approach, the two planets gravitationally scatter each other. One gains orbital energy and moves to a higher, more eccentric orbit. The other loses energy and falls to a lower orbit. This is a fundamental principle of gravitational interactions. Energy and momentum are conserved, so if one object gains energy, the other must lose it. If the encounter is energetic enough, the planet that gains energy can gain enough velocity to escape the star's gravity entirely. It's flung outward at speeds of 10 to 50 kilometers per second, fast enough to leave the star system and enter interstellar space. The planet that lost energy falls into a closer orbit around the star. It's the survivor. The ejected planet is the casualty. Computer simulations show that in systems with multiple giant planets, this process is common. Roughly 30 to 50% of giant planets formed in such systems get ejected at some point during the first 100 million years, while the system is still settling into stability. This has implications for what types of planets become rogues. Giant planets are most likely to be ejected because they're most massive and their gravitational influence is strongest. Rocky planets, like Earth, are less likely to be thrown out because they're less massive and their gravitational influence is weaker. However, rocky planets can be ejected if they're perturbed by a giant planet. A Jupiter-mass planet moving through the inner system due to migration can scatter smaller rocky planets into the outer system or eject them entirely. There's also another mechanism. If a planet is in a wide orbit around its star, and the star has a close encounter with another star, the gravitational influence of the passing star can strip the planet away. This is most likely to happen in dense star clusters, where close encounters between stars are more common. The Orion Nebula, where those first free-floating planetary mass objects were found, is exactly such an environment. It's a dense stellar nursery where young stars are packed closely together. Gravitational interactions between stars can disrupt planetary systems, liberating planets into interstellar space. So the rogue planet population is diverse. Some are gas giants, some are ice giants like Neptune or Uranus, some are rocky super-Earths, some might even be Earth-sized. They come from different types of planetary systems and were ejected through different mechanisms. The average rogue planet has probably been drifting for billions of years. If it was ejected early in its system's history, shortly after formation, it's been a rogue as long as its parent star has been shining. It has traveled vast distances through the galaxy, passing through different spiral arms, witnessing the birth and death of countless stars, but always alone, always in darkness.
Now, let's talk numbers. How many rogue planets actually exist, and how do we estimate this? The initial 2011 study by Sumi and colleagues found about 2 Jupiter mass rogues per star, suggesting around 400 billion such objects in the Milky Way. But that was based on only 10 microlensing detections. Statistical uncertainties were large. Since then, multiple surveys have refined the estimate. The K2 mission data analysis in 2021 suggested the number might be higher, possibly 4 to 20 rogues per star, depending on the mass range considered. Let's work through the calculation. The Milky Way contains approximately 200 billion stars. If there are 2 Jupiter mass rogues per star, that's 400 billion. But microlensing is only sensitive to planets roughly Jupiter mass or larger. What about smaller planets? Planetary formation simulations suggest that for every giant planet formed, multiple smaller planets are also created. If the ratio of small planets to giant planets is similar for ejected objects as it is for planets that remain in their systems, then we'd expect several Earth mass rogues for every Jupiter mass rogue. This is speculative because we can't easily detect smaller rogues with current technology. But if the ratio is 5 to 1, that's 2 trillion Earth mass rogue planets. If it's 10 to 1, that's 4 trillion. Let's take a conservative middle estimate. Say there are 1 trillion rogue planets in the Milky Way, spanning the full range of masses, from super-Jupiters down to Mars-sized objects. 1 trillion rogue planets. That's 5 times as many rogue planets as stars in the galaxy. It means the Milky Way is, in some sense, more of a planetary system than a stellar system. Planets outnumber stars. To put this in perspective, let's think about distances. The average distance between stars in our region of the galaxy is about 5 light-years, roughly 29 trillion miles, or approximately 47 trillion kilometers. If stars were grains of sand spaced 5 feet apart, the Milky Way would be unimaginably vast. But if there are 5 rogue planets for every star, then the average spacing between rogue planets is smaller, perhaps 3 light-years or so. They're still incredibly far apart by human standards, but they're closer together than stars are. If you could somehow travel through the galaxy at the speed of light, you'd encounter a rogue planet every 3 years on average. That's compared to encountering a star every 5 years. The galaxy is filled with these invisible worlds. Now, here's a thought experiment. Imagine humanity develops the technology to travel between stars. We send robotic probes or crewed missions to nearby star systems. As we're traveling through interstellar space, we might pass within a few billion kilometers of a rogue planet, close enough to detect it with sensitive instruments, close enough to study it. These rogues could serve as waypoints. They're sources of raw materials, potential refueling stops if we can mine ice for water or extract other volatiles. They might be scientifically fascinating, worlds with their own unique geological histories. A mission to a rogue planet might be easier in some ways than a mission to another star system. The rogue has no star to orbit, so you can approach it more directly. There's no intense radiation from a nearby sun, no need to time your arrival to match planetary orbits. Of course, the challenge is finding them. You'd need to know where a rogue planet is before you could target it, and since they're invisible, that requires either a lucky microlensing detection or perhaps future infrared telescopes sensitive enough to detect the faint heat signature from warm giant rogues.
Jupiter-mass planets remain warm for tens of millions of years after formation, slowly radiating away their internal heat. Young rogues are detectable in infrared. As observations improve, we'll refine our estimates of how many rogues exist, what their mass distribution looks like, and potentially where the nearest ones are located. But based on current evidence, the conclusion is clear. Rogue planets are not rare anomalies. They're a major component of the galactic population. They might outnumber stars. They certainly outnumber the planets we can see orbiting stars. This changes the inventory of objects in the galaxy. We used to think of the Milky Way as containing 200 billion stars, with maybe 1 trillion planets orbiting those stars. Now we need to add another 1 trillion or more rogue planets to that count. The galaxy is more complex, more crowded, more filled with worlds than we thought.
Let's dive deeper into how these rogues form, because the process reveals fundamental truths about planetary system architecture. We've mentioned gravitational ejection, but there are actually several pathways to creating a rogue planet. Pathway 1. Dynamical ejection. This is the most common mechanism. In a young planetary system with multiple giant planets, gravitational interactions cause orbital instabilities. Planets scatter each other. Eventually, one gets kicked out. Simulations show this happens most often in systems with 3 or more giant planets within about 20 astronomical units of the star. These systems are inherently unstable. Over timescales of millions of years, the planets perturb each other until the system undergoes a dynamical instability. When instability occurs, the outcome is often one planet ejected, 1 or 2 planets remaining on stable orbits. The survivors typically have eccentric orbits, unlike the nearly circular orbits in our solar system. Interestingly, many detected exoplanets have eccentric orbits, suggesting they're survivors of such instabilities. For every eccentric exoplanet we detect, there might be a sibling that was ejected and now roams as a rogue. Pathway 2. Stellar encounters. In dense stellar environments like young clusters, stars pass close to each other frequently. A close encounter can disrupt planetary systems. If 2 stars pass within a few hundred astronomical units of each other, their mutual gravity can strip planets from one or both systems. Planets in wide orbits are most vulnerable. They're weakly bound to their star and easily perturbed by a passing interloper. This mechanism is most effective in the first few million years of a star's life, while it's still in its birth cluster. Once the cluster disperses and stars separate, close encounters become rare. The Pleiades star cluster, visible as a small group of bright stars in the constellation Taurus, contains about 1,000 stars in a volume roughly 12 light-years across, or roughly 71 trillion miles, or approximately 114 trillion kilometers. Stars in such an environment pass within a few thousand astronomical units of each other every million years or so. That's close enough to disrupt outer planetary systems. Pathway 3. Formation in isolation. Some planetary mass objects might form not in a disk around a star, but directly from collapsing gas clouds, similar to how stars form. If a region of a molecular cloud is too small to form a star, but still manages to collapse under its own gravity, it could create a planetary mass object without ever being part of a stellar system. These objects are sometimes called sub-brown dwarfs, or isolated planetary mass objects. They never orbited a star. They formed alone. The distinction between a planet that was ejected and one that formed in isolation might seem semantic, but it has implications. Objects that formed in isolation might have different compositions or internal structures compared to objects that formed in disks and were ejected. Observationally, it's difficult to distinguish between the two. Both are free-floating planetary mass objects. Both are isolated and dark, but their formation histories are different. Pathway 4. Binary planet disruption. Here's an exotic possibility.
Suppose a planetary system forms two giant planets in a very close binary configuration, orbiting each other rather than orbiting their star independently. Such binary planets are theoretically possible, though none have been detected yet. If they exist, they could be disrupted by interactions with other planets in the system. The binary could break apart, with one planet remaining bound to the star and the other ejected. This is highly speculative, but it illustrates that there might be multiple formation channels we haven't fully explored yet. Understanding which pathway dominates matters for predicting the properties of the rogue population. If most rogues are ejected giants, they'll have compositions similar to Jupiter and Saturn, rich in hydrogen and helium. If many are ejected rocky planets, they'll have different compositions. If some formed in isolation, they might have properties unlike any planet in our solar system, potentially offering insights into alternative formation mechanisms.
The diversity of rogue planets is probably substantial. They come from different types of systems, formed at different times in the galaxy's history, and were liberated through different mechanisms. Each one has its own story. Let's talk about the technical challenges of finding these objects and what future observations might reveal. Microlensing is currently the best method, but it has limitations. The lensing events are brief, lasting hours to days. You need to be monitoring millions of stars constantly to catch events as they happen. The events are not repeatable. Once a rogue passes between Earth and a background star, it's gone. You can't go back and study it further. Microlensing tells you the mass of the object and approximately where it is, but not much else. You don't get spectroscopic data. You don't learn about composition or atmospheric properties. For young, warm rogues, direct infrared detection might be possible. Jupiter mass planets remain warm for tens of millions of years after formation. They glow faintly in infrared wavelengths, with temperatures around 900 to 1300 degrees Fahrenheit, or about 500 to 700 degrees Celsius for the youngest objects. If a young rogue is within a few hundred light years, sensitive infrared telescopes could detect it. The James Webb Space Telescope has the sensitivity to detect warm Jupiter mass rogues within about 100 light years, or roughly 588 trillion miles, approximately 947 trillion kilometers, if it knows where to look. The challenge is searching. The sky is large. A blind search would take years. But if microlensing surveys provide rough locations, follow-up infrared observations could characterize warm rogues. For older, cooler rogues, detection becomes essentially impossible with current technology. A rogue planet that's billions of years old has cooled to near the temperature of interstellar space. It emits virtually no radiation. It's invisible. The only way to find such objects would be through their gravitational effects. If one passed very close to the solar system, perhaps within 1 light year, we might detect its gravitational perturbation on comets in the Oort cloud or on spacecraft in the outer solar system. But the probability of such a close passage is low. Space is vast, and even though rogues are common, the distances between them are still enormous. There's one other possibility. If a rogue planet happens to pass in front of a background star as seen from Earth, it would cause a tiny, brief dimming, similar to a planetary transit. But unlike a normal transit, this would be a one-time event. The rogue isn't orbiting the star, it's just passing in front of it. Survey missions that monitor millions of stars might detect such events, but distinguishing them from other transient phenomena would be challenging. You'd need to verify that the dimming wasn't caused by a variable star, an eclipsing binary, or instrumental noise. The Nancy Grace Roman Space Telescope will revolutionize rogue planet studies. Its wide field of view and sensitivity to microlensing will allow it to detect rogues down to Mars mass, potentially finding thousands of them. By analyzing the distribution of detected rogues, their masses, and their spatial distribution in the galaxy, astronomers will constrain formation models. How many rogues exist? What's the mass function? Are they clustered in certain regions or uniformly distributed? These observations will also help address a fundamental question. Are rogues primarily ejected planets, or do some form in isolation?
The answer has implications for planetary formation theory and for understanding the mass spectrum of objects in the galaxy. In the more distant future, advanced infrared telescopes or even gravitational wave detectors might provide new ways to find rogues. If rogues are as common as we think, they contribute to the gravitational potential of the galaxy. Their cumulative effect might be detectable through their influence on galactic dynamics. And if humanity ever develops the capability to travel to nearby star systems, we might stumble upon rogues along the way. A probe traveling to Alpha Centauri might pass within detection range of a rogue planet midway through its journey. Serendipitous discoveries could characterize rogues in ways impossible from Earth.
The existence of a large rogue population has profound implications for how we understand planetary systems. First, it means planetary system formation is more violent and chaotic than simple models suggest. If 30 to 50% of giant planets get ejected, then the systems we observe today are survivors of intense dynamical evolution. Our solar system, with its relatively circular, stable orbits, might be atypical. We might be lucky. Perhaps most systems undergo violent instabilities that eject some planets and leave survivors on eccentric orbits. This connects to observations of exoplanets. Many detected exoplanets have eccentric orbits, some with eccentricities above 0.5. These are probably survivors of dynamical instabilities. Their ejected siblings are now rogues. Some exoplanets are on extremely close orbits, circling their stars in just a few days. These hot Jupiters probably formed farther out and migrated inward through interactions with the protoplanetary disk or through gravitational scattering. As they migrated, they might have ejected other planets. The rogue population is a record of this violence. Each rogue represents a planetary system that underwent instability. By studying rogues, we learn about the processes that shape planetary system architecture. Second, the existence of rogues affects the mass budget of the galaxy. If there are 1 trillion rogue planets averaging, say, 5 Earth masses each, that's 5 trillion Earth masses of material in rogues. That's a significant fraction of the total mass in planets. Most of the heavy elements in the galaxy are locked up in stars and their remnants, but a substantial fraction is in planets, both orbiting stars and rogue. Understanding the rogue population helps us understand the distribution of heavy elements in the galaxy. Third, rogues might play a role in seeding life across the galaxy. This is highly speculative, but consider the possibility. If a rogue planet with a subsurface ocean harbors life and that planet passes through a star system, it could potentially transfer biological material. Meteorite impacts on the rogue could eject material into space. Some of that material might be captured by planets in the star system. This is panspermia, the idea that life could spread between worlds. It's usually discussed in the context of life transferring between planets in the same system, like Earth and Mars, but rogues could carry life between star systems, potentially spreading biological material across the galaxy. This is extremely unlikely for any individual rogue, but if there are trillions of them and they've been wandering for billions of years, perhaps some improbable events have occurred. Again, this is speculative. We have no evidence of life on rogues or of panspermia, but the existence of a vast rogue population opens up possibilities that weren't on the table before. Let's talk about the rogues that might be close to us. Where is the nearest rogue planet, and could we ever visit it? Based on the estimated density of rogues in the galaxy, the nearest one is probably within 10 to 20 light-years of the Sun, roughly 59 to 118 trillion miles, or approximately 95 to 190 trillion kilometers. That's farther than the nearest known star system, but not by much. We have no way to know where it is because it's invisible, unless it happens to cause a micro-lensing event that we detect, or unless future infrared telescopes spot it. The nearest rogue remains unknown. But let's imagine we find one. Say it's 15 light-years away, a Jupiter-mass rogue that's young enough to still be warm and detectable in infrared. What would a mission look like?
With current propulsion technology, reaching a target 15 light-years away would take tens of thousands of years. The Voyager probes, traveling at about 17 kilometers per second, would need roughly 250,000 years to cover that distance. Future technologies could be faster. Nuclear pulse propulsion, using small nuclear explosions for thrust, might achieve 3 to 5% of light speed. At 5% of c, the journey would take 300 years, still prohibitively long for human missions, but perhaps feasible for robotic probes designed to last centuries. Laser-pushed light sails, using powerful lasers to accelerate lightweight probes, might reach 10 to 20% of light speed. At 20% of c, the trip would take 75 years. A probe launched today might reach the target within a human lifetime. Upon arrival, the probe would study the rogue in detail, image its surface or cloud layers, measure its mass, composition, and internal structure, search for moons. If the rogue is icy and has a subsurface ocean, the probe might even search for signs of life. Deploy a lander to drill through the ice, like proposed missions to Europa. Look for organic molecules, biosignatures, anything suggesting biological activity. This is science fiction today, but perhaps achievable within the next century or two. The existence of a large rogue population means there are potential targets for such missions, closer than many star systems. Rogues could be humanity's first destinations outside the solar system. Before we visit another star, we might visit a rogue drifting through interstellar space. We've been discussing rogue planets, but there's another possibility that's equally fascinating: rogue moons. When a planet is ejected from its system, it might take its moons with it. Jupiter has 95 known moons. Saturn has 146. If a Jupiter-like planet is ejected, some or all of its moons might remain bound to it. The ejection event is violent, and tidal forces could strip away the outer moons, but moons in close orbits, those within a few planetary radii, would likely survive. They'd continue orbiting the rogue planet as it drifts through interstellar space. This creates a miniature system, a rogue planet with moons wandering the galaxy together. The moons would experience tidal heating from the planet's gravity, similar to how Jupiter heats Io and Europa. This heating could keep subsurface oceans liquid even on moons orbiting a rogue planet. In some ways, moons of rogue planets might be better habitats for life than the rogues themselves. Tidal heating provides a steady heat source independent of the planet's internal radioactive decay. A moon like Europa, if ejected with Jupiter, could maintain its subsurface ocean for billions of years. The galaxy might contain billions of rogue moons orbiting rogue planets, each one a potential habitat, each one a frozen world with a liquid ocean beneath the ice. If life exists on these moons, it would be truly isolated. The moons orbit a planet that orbits nothing, drifting through interstellar space. Any civilization that arose on such a moon would have no concept of stars as suns. They'd see distant points of light in their sky, but no bright star dominating their heavens. They'd live in perpetual darkness, powered by tidal heating and geothermal energy. Their entire biosphere would be chemosynthetic, based on chemical energy rather than sunlight. They might never discover fire because there's no oxygen-rich atmosphere. Their technological development would follow a completely different path. This is highly speculative, but it's a possibility we can't rule out. If the galaxy contains trillions of rogue planets, and some fraction have moons, and some fraction of those moons have subsurface oceans, then perhaps millions or billions of moons harbor life. We'd never detect such life from Earth. We can barely detect the rogues themselves. Detecting moons around rogues is beyond current technology, but they might be out there. Entire ecosystems thriving in hidden oceans, completely unaware of the larger universe. There are other exotic possibilities. What if a planet is ejected during a supernova explosion? The planet might be bathed in intense radiation and shockwaves. Material from the supernova could contaminate the planet's surface. If the planet survives, it would carry with it traces of its violent past, perhaps enriched in unusual isotopes or bearing scars from the explosion. What if a rogue planet has a very eccentric orbit around the galactic center, bringing it close to the galactic disk in some regions and far above the disk in others? During its journey through dense regions of the disk, it might interact with molecular clouds, potentially accreting additional material. What if a rogue planet happens to pass very close to a star, perhaps within a few astronomical units, and gets gravitationally captured? It would transition from rogue planet to normal planet, suddenly finding itself in orbit around a sun after billions of years of wandering. Computer simulations show this is rare but possible. A rogue passing through a planetary system could be captured if it loses enough energy, perhaps through interaction with other planets in the system. It might settle into a distant, eccentric orbit. If this happens, the rogue would suddenly receive light and heat from its new sun. If it has a frozen surface, that ice would begin to sublimate, creating a temporary atmosphere. If it has subsurface oceans, the surface might warm enough for the ice to melt, exposing the ocean to space before it refreezes. A captured rogue might bear the chemical signatures of its time in interstellar space. Its composition might differ from other planets in the system. It might have isotopic anomalies. It would be a foreign object, an immigrant from another part of the galaxy. Astronomers sometimes detect exoplanets with unusual orbits or compositions. Could some of these be captured rogues? It's possible, though difficult to prove. The planet's properties might hint at its history, but definitively establishing that it was once a rogue would be challenging.
Let's zoom out and consider what rogue planets tell us about the universe at large. First, they reveal that planet formation is a lossy process. Not every planet that forms ends up in a stable orbit. Many are cast out. The systems we observe are the survivors. The rogues are the casualties. This has implications for estimating the total number of planets in the galaxy. If we count planets orbiting stars and estimate there are 1 trillion such planets, we need to add another 1 trillion or more rogues. The total planetary population is at least twice what we'd estimate by counting only orbiting planets. Second, rogues demonstrate that planets can exist in environments far removed from their formation sites. A planet that formed 30,000 light-years from the galactic center might now be 50,000 light-years away, having been ejected and wandered for billions of years. This means the current spatial distribution of planets doesn't necessarily reflect where they formed. Chemical signatures that suggest formation in one environment might be found in planets currently in completely different environments. Third, the existence of rogues shows that planetary systems are dynamic over long timescales. We tend to think of planetary systems as static, with planets in fixed orbits that persist indefinitely. But the rogue population proves that systems can undergo dramatic rearrangements even billions of years after formation. Late-stage instabilities can eject planets, stellar encounters can disrupt systems, planets can migrate. What we observe today is a snapshot. The configurations we see might not last. Fourth, rogues contribute to the mass and structure of the galaxy. With trillions of them, they collectively represent a significant mass reservoir. They don't emit light, so they don't contribute to the galaxy's luminosity, but they do contribute to its gravitational potential. They're part of the missing matter in galaxies, though a relatively small part compared to dark matter. But they're real, baryonic matter, not exotic dark matter particles. Fifth, the rogue population affects galactic ecology in subtle ways. As rogues drift through the galaxy, they occasionally pass through molecular clouds or dense regions of the galactic disk. Their gravity can perturb gas clouds slightly, potentially triggering or inhibiting star formation in local regions. These effects are tiny for any individual rogue, but cumulative effects over billions of years and trillions of rogues might be measurable. They contribute to the stirring and mixing of galactic material. Finally, rogues change our perspective on habitability. We usually think of habitability as requiring a planet in the right orbit around a star. The habitable zone, where temperatures allow liquid water, is defined relative to the star's luminosity. But rogues with subsurface oceans show that habitability doesn't require starlight. Internal heat sources suffice. This expands the range of potentially habitable environments far beyond traditional habitable zones.
If life can arise and thrive in subsurface oceans independent of stars, then the volume of habitable space in the galaxy is vastly larger than we thought. Not just the thin shells around stars where temperatures are right, but potentially throughout interstellar space on rogue planets with subsurface oceans. This doesn't mean life is common on rogues. The origin of life might still require specific conditions we don't fully understand, but it means the opportunity space is larger. Despite progress in understanding rogues, many questions remain unanswered. How many exist? Current estimates range from hundreds of billions to several trillion. The uncertainty is large. Better microlensing surveys will narrow this range, but definitively counting rogues requires detecting them, and most are too faint and cold to detect with current technology. What's the mass distribution? We know Jupiter mass rogues exist. We suspect smaller rogues are more common, but we can't detect them yet. The ratio of small to large rogues affects the total population estimate significantly. How many have moons? If rogues can retain their moons, the number of rogue moons might exceed the number of rogues, but we have no observations confirming moons around rogues. Detecting them requires resolving rogues at high spatial resolution, which is beyond current capabilities. Do any have atmospheres? Giant rogues probably have thick hydrogen and helium atmospheres, similar to Jupiter, but smaller, rocky rogues might have lost their atmospheres to space over billions of years, or they might retain atmospheres kept warm by internal heat. We don't know. Could any harbor life? This is purely speculative. We have no evidence of life on rogues, but if subsurface oceans exist and are kept liquid by internal heat, life is at least plausible. Answering this requires missions to rogues, which are not feasible with current technology. Where do they travel? Rogues orbit the galactic center, like stars, but their orbits are probably more eccentric, taking them through different regions of the galaxy over time. Modeling their orbital evolution helps predict where rogues might be concentrated today. Can they be recaptured? The probability of a rogue being captured by a star is low but non-zero. If captures occur, captured rogues might be detectable as planets with unusual orbits or compositions. No confirmed examples exist yet, but they might. What happens when two rogues collide? Space is vast, so collisions are rare, but over billions of years and with trillions of rogues, some collisions have probably occurred. What's the outcome? Do they merge, shatter, ricochet? We don't know. How old are most rogues? If most were ejected during the first 100 million years of their planetary system's histories, then the typical rogue is nearly as old as its parent star. But late-stage ejections also occur. The age distribution of rogues reflects the history of planetary dynamics across cosmic time. Can we detect biosignatures on rogues? If a rogue has an atmosphere maintained by geothermal heat, it might contain gases that indicate biological activity, like methane or oxygen. Detecting such signatures requires spectroscopy, which in turn requires detecting the rogue and characterizing its atmosphere. This is far beyond current technology. These questions will drive future research. The Nancy Grace Roman Telescope will answer some. Future infrared missions will answer others. Some questions might require interstellar missions to rogues, which are far in the future. But progress will continue. Each new detection refines our understanding. Each theoretical model improves predictions. Gradually, the picture comes into focus. Let's consider what rogue planets mean philosophically. What do they tell us about our place in the universe? First, they're a reminder of cosmic violence. Planetary systems form chaotically. Planets collide, scatter each other, and are sometimes ejected into interstellar space. The universe isn't gentle, it's violent and dynamic. Our solar system seems stable, with planets in nearly circular orbits that have persisted for 4.5 billion years. But we might be lucky. Many systems undergo violent instabilities. Some of our planets might have been ejected early in the solar system's history. We might be survivors. Second, rogues challenge our definitions. What is a planet? If it doesn't orbit a star, is it still a planet? Astronomers debated this when defining the term planet in 2006, ultimately deciding that planets must orbit stars. Free-floating objects are not planets by this definition. But physically, rogues are planets. They formed like planets, they have planetary masses and compositions. The fact that they don't orbit stars seems like an arbitrary distinction. This reflects the difficulty of categorizing objects in the universe. Nature doesn't care about our definitions. Objects exist across a continuum of masses, compositions, and orbits. We draw lines for convenience, but the universe is more complex than our categories. Third, rogues illustrate the diversity of cosmic environments. We often imagine planets as places like Earth, orbiting suns with days and nights, seasons, predictable cycles. But rogues experience none of this. They exist in perpetual night, drifting through unchanging darkness. If life exists on rogues, it evolved in a completely different context from life on Earth. It would have no concept of day or night, no seasons, no sunlight. Its energy sources would be geothermal or chemical, not photosynthetic. This challenges our assumptions about life. We tend to think of Earth-like conditions as necessary, but life might be more flexible. It might arise in subsurface oceans on rogues, in the clouds of gas giants, in exotic chemical environments we haven't imagined. Fourth, rogues are a reminder of cosmic timescales. A rogue planet ejected 8 billion years ago has been drifting for most of the universe's history. It's traveled thousands of light years from its birth site. It's witnessed the evolution of the galaxy, passing through spiral arms, molecular clouds, and voids. If such a rogue has a subsurface ocean with life, that life has existed in isolation for billions of years, evolving independently, potentially becoming highly complex without ever interacting with life from other worlds. The timescales involved are staggering. Human civilization is 10,000 years old. The oldest human structures are a few thousand years old. Rogues have existed millions of times longer. They're ancient wanderers, carrying with them the history of their formation and ejection. Fifth, rogues are invisible neighbors. Right now, there are probably dozens or hundreds of rogue planets within 100 light years of Earth. We can't see them. We don't know they're there, but they're out there, drifting silently through space. This is humbling. There's so much we can't see. The universe is more complex than what we observe directly. Dark matter, dark energy, black holes, and now rogue planets, all invisible or nearly so, all shaping the cosmos in ways we're only beginning to understand. Finally, rogues pose ethical questions for the distant future. If humanity develops interstellar travel and encounters rogues, what are our responsibilities? If a rogue has a subsurface ocean with life, is it ethical to disturb it? Should we study it, colonize it, leave it alone? These questions seem remote, but they're extensions of debates we have today about exploring Europa or Enceladus. If life exists in alien environments, how do we balance scientific curiosity with ethical considerations? Rogues might be the first extraterrestrial habitats we encounter. Our decisions about how to approach them will set precedents for how humanity interacts with alien life and environments. We started this journey with a simple realization. The galaxy contains invisible worlds drifting through interstellar space, planets without suns, rogues. Through our exploration, we've learned that these rogues are not rare, they're common, they might outnumber stars. The galaxy contains trillions of rogue planets, spanning the full range from Mars-sized rocky worlds to super Jupiters many times the mass of our largest planet. We've learned that rogues form through violent processes, stellar counters in dense clusters, perhaps direct collapse in molecular clouds. Each rogue has a story of formation and ejection, a history written in its composition and internal structure. We've discovered that rogues can have moons, and those moons might harbor subsurface oceans kept liquid by tidal heating. Life might exist on rogue worlds, thriving in hidden oceans, completely independent of starlight. We've explored the challenges of detecting rogues. Microlensing surveys have found a handful. Future telescopes will find thousands. But most rogues will remain invisible, too cold and dark to detect, drifting unseen through the galaxy. We've considered what rogues mean for our understanding of planetary systems. They're evidence of chaotic dynamics. They're a reminder that not every planet survives. They expand the definition of habitable environments beyond traditional habitable zones around stars. And we've reflected on the philosophical implications. Rogues challenge our categories. They illustrate cosmic violence and timescales. They're invisible neighbors, ancient wanderers carrying with them unknown histories. The nearest rogue planet might be closer than the nearest star. It might be within 10 or 20 light years, drifting silently through the darkness. We don't know where it is, we can't see it, but it's out there. Perhaps someday we'll find it. A future mission, robotic or crewed, might encounter a rogue on the journey between stars. We'd study it, learning about its composition, its history, its moons. If it has a subsurface ocean, we might search for life. That day is far in the future. For now, we can only observe rogues through microlensing and imagine what they're like. But the knowledge that they exist, that the galaxy is filled with dark wanderers, changes how we see the cosmos. The universe is not just stars and galaxies, it's also the spaces between. And those spaces are not empty, they're filled with worlds. Dark, silent, ancient worlds drifting through the galaxy. Worlds we're only now beginning to discover. The cosmos awaits, and somewhere out there in the darkness, a rogue planet drifts alone, carrying with it the story of its formation, its ejection, and its billions of years of wandering. We may never see it, but now we know it's there. That's the power of science, to reveal what cannot be seen, to understand what cannot be touched, to illuminate the darkness with knowledge. The universe is vast, the rogues are many, and the journey of discovery continues.